yes. You have all the recorded versions on uploaded on YouTube. If you go to the RL course web page, there's this problem solving tab. There you have all the recorded lectures as well as the slides that I'm presenting. You will
Oh,
find all
can
of
you
that.
just give us a URL for the same so that we can just read?
If you go to your reinforcement learning, like wherever you are doing your NPTEL course, the SWAYAM portal. So wait, I'll just show you here. So this is like my login. You just go log in there, go to the course homepage. There you
Okay.
have this problem. There you have something known as problem solving session. So every week we take this problem solving sessions for each week that has happened, and you'll find the respective YouTube videos uploaded over there.
Okay, sir.
Okay,
Thank you.
okay, okay, no problem. Okay, so it's 7:05. I think we should start. So hi everyone, welcome to the week 6 uh, tutorial session for RL course. Uh, so my name is Manav. I'm one of the TA for this course. If you have any queries related to course or you just want to you know connect with me, you can feel free to reach out to me. Uh, what my plan is, we'll quickly have a look at what all has been covered in week 6 so far. I'll do a quick uh, summary of all that has been covered, and then we'll look at two codes that I have in mind. One of the implementation was already presented in Aniket's class, so that will be a repetition. And the second one is a simple implementation of the cliff world problem. Okay, so we'll see both of these things. Okay, so let's start. So uh, week 6 started off with the introduction of off-policy Monte Carlo, right? And to understand off-policy Monte Carlo, it's important to understand something known as importance sampling. So what happens in Monte Carlo is, let's say you want to estimate a distribution that you have. The way you estimate the distribution is by drawing samples. Okay, you randomly select samples from the distribution, unless and until you have good number of samples, so that you do a simple average over it, and then uh, you have the corresponding distribution. Okay, this is the basic idea of Monte Carlo, and this works because you have the central limit theorem proving its convergence, that eventually whatever samples I'm drawing will converge to the probability distribution that I'm looking at. Okay, so this is the Monte Carlo method. But what happens is, when I'm drawing a lot of samples in trying to estimate something, there will be a lot of variations that a lot of variance that happens because of the stochasticity of the samples that I'm drawing. Okay, so to counter on that, people use in statistics some variance reduction techniques. One of them is importance sampling. So what happens is, I can maybe show this diagram. So let's say you want to estimate this blue curve. Okay, so this is the probability distribution that you want to estimate. And then initially you have a uniform distribution. You start sampling points randomly, you evaluate that and do some updates. So if you want to estimate this blue line, so your initial estimate is a uniform distribution. So you see, it's some sort of an okayish distribution to start off with, because it's uniform means you are sampling randomly. But it would be better, right, if I have a distribution which is sort of mirroring this distribution, some sort of an umbrella distribution over it. So if I have this kind of an umbrella distribution, then sampling from that point would help me like get the estimation faster with lower variance. Okay, and the third diagram is obviously a bad initialization. If I take a PDF which is totally in the opposite direction, then the variance would be huge, and it will eventually take me a lot of time with a high uh, variance to reach that particular part. Okay, so the trick here is to identify this good umbrella distribution, so that if we sample from that distribution, we are like guaranteed to converge faster with lesser variance, right? So important sampling happens. Like important sampling is just this simplistic mathematical trick. So let's say I want to find out the expectation. Oh, So I want to find out the expectation of f of x where I'm sampling x with probability p, right? So if my probability p is something very basic like a uniform distribution, I want to change it to a distribution which is q of x. So what I do is I uh, multiply and divide by qx. So see how this looks like is you have this. So if you uh, do the rollout, you it looks something like this. It looks like pxfx, right? So I just multiply and divide by qx. So it's some probability distribution, and the assumption is that qx is not equal to 0. Okay. If I do that, so I reach this step over here. That means now I'm basically sampling from the distribution x from the distribution q, but instead of estimating the quantity f of x, now I'm estimating the quantity fx times px by qx. So this new term over here, this is known as the importance sampling factor. So based using this trick, you can uh, switch your distribution so that you reduce the variance and try to mirror the distribution that you're trying to emulate, right? And if okay, so this can be approximated like this. Okay, so this is I'm just drawing random samples and averaging over it. So this is f of xi times pxi by qxi. Okay, so this is my simple importance sampling. And weighted importance sampling is here. I'm doing a simple average. Instead of doing a simple average, to make it more general, I can do a weighted average. So my weighted for my weighted importance sampling, the equation looks something like this. Mhm. Okay, so here I haven't taken this the importance to be 1 by n, but the importance here is this denominator term, which is pxi upon qxi. I hope it's legible what I'm writing. Uh, Okay, so this is the basic idea of importance sampling. Now the idea here is, since importance sampling is useful when we are trying to do some Monte Carlo estimation of a probability distribution, the idea is to take this equation and put it in our Monte Carlo approach for reinforcement learning. Okay, so to do that, we have to define what is f of xi, what is px, what is qx, and what is x. Okay, so if we do that, so we can typically use it for our Monte Carlo of of policy Monte Carlo, right? Uh, so here we'll define two things. Okay. So pi is the policy that I want to estimate, and mu is the policy that I want to follow. Okay. It's a behavior policy that I want to learn over time. Some sort of an umbrella behavior. Okay. It need not be the exact thing that I want to learn. It need not be the exact pi star that I'm estimating, but mu is some sort of a better PDF. Okay. Which is helpful for me later on. Okay. So xi is basically a trajectory. So if this trajectory is, let's say you have a start position, we take action A0, then at R1, then S1, A1, R2, and so on. Okay, so this is the trajectory that you have. Like you have a start state, you draw out random trajectories. Okay, because in Monte Carlo, you draw out random trajectories, and based on that, you do your updates, right? So if you do that, so my P of X, if you go back to the previous equation, my P of X would look like probability of being in state as 0, then the transition probability of moving to action A0 from state as 0, then sorry, this is the probability of taking action A0 given state as 0, then moving to state S1 given S0 A0, then I have pi of A1 by S1 and so on. Okay, So this is my P of xi. Similarly, my behavioral policy, Q of xi, should look something like this. So instead of pi, you use mu. This is A0, S0, P of S1, S0, A0, mu A1, S1, and so on. Okay. So the thing is, in Monte Carlo, you typically don't have access to the probabilities. You don't have the access to the model. By model, I mean the state transition probability. So these p values that you have over here, this stuff, you don't have access to this in Monte Carlo. Okay, but here in the equation, in px in computing p of x and q of x, you need those values. But when I'm doing the ratio of that, so everything cancels out. If you can see, so if I take the ratio, it looks like this. Okay, and I have to write it down. Should look something like this. Okay, the t is the time horizon of the trajectory that I'm looking at, and this is the ratio of pi of aj given sj divided by mu of aj by sj. Okay. So once you have that, once you have this quantity, so now what you are trying to estimate here is this function, right? And this function, where f of x is nothing but the return that I'm trying to generate over time. So this quantity corresponds to the return. Okay. So if I look at the expectation of f of x, that f of x is the return value. So this typically corresponds to my value function, right? My v pi of s. So if I were to do the policy evaluation and I substitute everything in here, so my for my importance sampling policy evaluation, this is what I get. Okay, note this is for evaluation because I'm computing the V pi, right? And once you have done the evaluation, you update the policy and so on. You do the typical Monte Carlo updates. Okay, so this is the basis of your off policy Monte Carlo. Okay, and okay, so with that we move to this upper confidence trees. Okay, so in Monte Carlo, you had random sampling. So this is typically referred to as rollouts. Okay, so let's say you are in a simulation. So you start at some state S and you take a bunch of different actions, eventually ending up at the goal state. Okay, so this is what you. So once you take generate different trajectories, you take an average over different steps, different actions that you're taking over time, and the different states that you're reaching. So over time, you would also generate an estimate of the policy. And the good thing about this is that this rollout method, this guarantees that the rollout policy execution is at least as good as the policy pi, or better if pi is not pi. So conservatively speaking, it is as good as the policy that I'm estimating. Okay, even using your simple value iteration, policy iteration stuff. And if it and it's better if the pi that I'm the estimated pi that I have right now is not the optimal policy, then the rollout method improves on that and gives me the optimal policy. Okay, so this is the advantage of using rollout methods. Uh, okay. So typically what you do is, and once you have the rollout and you want to look at the Monte Carlo, sorry, you want to do the you want to look at the upper confidence trees. So what you do is you have, let's say, some, you know, no, sorry. So let's say you have some initial state, you take some trajectory, here you take some different trajectory and some trajectory and so on. Okay. So this algorithm basically gives you a method. Okay. to evaluate or do the learning on such kind of policies, but with an upper confidence bound. Okay, so this is an algorithm for Monte Carlo tree search kind of a thing. Okay, so the algorithm looks like this. So this is the search algorithm. So the algorithm is, if I'm at the terminal state, then return zero. This zero is just an abstraction. This could very well be my r of capital T, which is like the reward you get on reaching the terminal state. But let's assume that it's zero for here. If it's a leaf state, then you return the evaluation of that state. So typically what happens is you don't, let it go till the end of the till the terminal state, because you have limited computational capabilities. So, typically stop it at some random interval and you call it as a leaf node. If you are reaching at a leaf node, then do some sort of a future prediction kind of a thing. So you do this eval state if you are reaching at a uh, leaf state. Otherwise, what you do is you select action based on the samples that you're drawing. This is not there's no epsilon greedy here, right? You're drawing samples and uh, okay, so you select actions, and then once you simulate that, you have your next states and the rewards, and you do the queue update. So this is a recursive algorithm that is happening. So you have the reward, then so, you have the reward, and then gamma of the next state. Okay, because uh, I only get a reward if I'm at a terminal state or a leaf state, and then you update the value accordingly, and then return the queue value. So once you have that, so my UCT algorithm typically looks like this. So the select action. So this part I'm looking at. Okay, so the select action is the way you do that is you have the estimated value function that you have at that particular time instance. So the estimated value function plus you are adding this uncertainty term over here. So this is something that you had seen in the upper confidence bound algorithm, the UCB1 algorithm, but the constant before that was 2. Now it has changed to CP. So the CP is the exploration parameter. So if you want to explore more, you want to keep C higher, and if you want to explore less, you decrease C. But typically the CP is greater than 1. Okay. So this is the idea behind your UCT. And if you look at it intuitively, what you are doing is trying to sort of convert whatever you had done in your bandit algorithm to a full RL problem. So the intuition you're bringing from different parts, you're using the idea of the upper confidence bound, you're using the idea of your Monte Carlo, and uh, based on that, you're defining this UCT algorithm, right? Next up, we have this temporal difference method. So before that, we have uh, done two different. We have looked at two different kinds of updates or methods to deal with reinforcement learning problem. One is the dynamic programming approach, and the other is the Monte Carlo approach. So what happens in dynamic programming is you have access to the entire model itself, so you know the probabilities with which you can take certain actions and the all possible next states that you can reach taking the actions and so on. So you have some sort of a branch out tree. So it's a so when you're trying to do an update, so let's say this red circle represents the states, this black dot represents the action. So if I want to, compute the value function, I just need to look at the next state ahead. I just need to look one step ahead, and whatever value I have, I take that, and based on that, I make an update. And I can do that because I have, I can do that because I have access to the set of possible next states that I can go to. If I have this much uh, access with me, then I can basically do something known as a full backup. And this method uses bootstrapping. So by bootstrapping, what we mean is when you're trying to, uh, uh, bootstrapping is when you're trying to basically estimate something that is happening in future based on an estimate that you have in the present time. Okay. So you're not taking the absolute value, but rather making some future estimate over making some future estimate. So that is bootstrapping. And the other approach is the Monte Carlo approach. So in that you don't have a full backup because you're trying to draw samples, and whatever backup you're doing is sort of online. It's fully online. So whatever backup that you have, it's not the full backup, but the backup that you get from drawing out samples. So this is a sample backup, and there is no bootstrapping as such because you don't have any estimate that you are on which you want to do your updates. So all you have is the true sampled values. Okay. So TD0 or temporal difference method, you know, combines the advantages what DP what dynamic programming gives, which is bootstrapping, and what Monte Carlo gives, which is sample backup. So it's basically taking the advantages of both these two approaches. And if I were to define it, this is sample backups plus bootstrapping. Okay, so this is my TD algorithm. So what you're trying to do is you are, let's say, should be the same color. So you're just looking one step ahead uh, based on the, I mean, you're just, whenever you're doing samples, the update that you do is you're just looking one step ahead. And after that, you do bootstrapping after looking one step ahead. So this is the idea behind your temporal difference algorithm. Okay, so this is the way backup happens. Here you do a sample backup. This is some sort of a full backup. Okay. And the reason why this is known as temporal difference is because you're typically looking at the value at t plus 1 to update the value at time t. So you are looking one step ahead to update the value at time t. So look at value t plus 1 to update value at t. So this is the idea behind your temporal difference method. And the way it works is, so let's say this is my value function. So if I want to define the, this is my value function, okay. So if I want to define the stochastic averaging method for my value function, so you have this age-old method that we have looked at in week 1 or I think in week 2. Then this is the g of t minus v of modulus, right? So if I want to update my value function and I want to, instead of maintaining histories, I want to do it like as and when I get the new updates, like incremental updates. So the way this happens is you have the new estimate is given by old estimate plus some step param. This is a step parameter. This is the target minus the current estimate, or rather the old estimate, right? Okay, so this is the main idea behind your stochastic averaging. So if I look at the MC version, so what happens is I need to in MC, I typically have access to this entire G of t because I draw samples till I reach the end of the till I reach the terminal state. Okay, so my G of t in case of Monte Carlo is RT plus 1 plus gamma RT plus 2 plus dot dot dot. Look like- Okay, so this is my Monte Carlo return. Now, if I were to you know uh, introduce the idea of TD to this, so what I can write this as gamma times G of t plus 1. Okay, so TD basically makes this assumption that whatever G of t plus 1 that I have, I approximate it using my value function. Okay, so this is the idea behind my uh, TD method. So if I were to write it, uh, should look like v nu s is equal to, I'm just substituting this over here. So I hope I haven't missed anything. So this entire thing is known as my TD backup. Okay, and this term over here inside this, you have a special name for it. This is known as the TD error. Okay, so this is the error term, right? This is the target minus the estimate. So you're trying to get reach closer and closer to the target with each estimate. So you have this delta t parameter to represent this TD error thing. So this is your TD zero algorithm. Next up, we have SARSA algorithm. So what happens in SARSA is it's an on-policy algorithm. So you basically act epsilon greedily when you're drawing samples, and you're trying to update the policy as and when you draw the samples. And the way this happens is instead of the value function, you take up the Q function. So you start up with some arbitrary Q function. You pick the initial state. You pick action AT in state ST according to Q of ST. So you do this epsilon greedily. So you have some epsilon parameter. Let's say this is 0.1. So you have some epsilon parameter because you want to encourage exploration. Then you apply AT and sample the next state and the reward. Then you also pick the next action according to the new Q value. This also happens epsilon greedily. And then you do the then you solve this Bellman equation for the Q function. And after that you do this continuously until you reach convergence. Okay. So you see what happens in SARSA is you are solving the Bellman equation. Okay. And because you're solving the Bellman equation, that means you need to have the policy when you're solving this, because uh, here instead of your value function, you're taking your value function is okay. So your v of st plus 1 is the okay, this is a prime is t plus 1 q of st plus 1 a prime, right? So this is your value function that you want. But instead of that, instead of taking this entire thing, instead of taking basically the expectation with respect to pi of your q of st plus 1, okay, what you're doing is you're drawing a sample. instead of taking the entire estimation, you're drawing a sample from that and doing this. And the idea is if you keep on drawing more number of samples, eventually you will end up with this expectation with time. Okay. So this is the general idea behind SARSA. So this happens when you solve the Bellman equation. So here you have two hyperparameters. One is the epsilon that you need to look at to look at the exploration exploitation part, and also the alpha parameter, because with time you also need to decrease cool off your alpha parameter. Okay, so this is the idea behind your SARS algorithm. This is a non-policy algorithm because you have a policy on which you're drawing your samples from, or on which you're picking your actions from, right? So you have a policy and you have a strategy also to uh, sample from that policy, be it epsilon greedy, be it softmax, or any other algorithm. uh, Next up is the Q learning. Is Q learning. So the way Q learning is different is from SARSA is, in SARSA we are solving the Bellman equation, but in Q learning we are solving the optimal Bellman equation, right? This is the key difference. And another difference is that SARSA was an on policy method, but Q learning is an off policy method. So you don't typically need a policy. You don't need to have you don't need to make updates on the current policies that you're sampling from, right? So my Q star is defined as the expectation of RT plus 1 plus gamma of V star ST plus 1, right? So instead of V star, I would like to represent everything in terms of Q star. So my V star is simply max of A prime Q ST plus 1 A. Okay. So V star basically tells me that if I'm at state S, I should take the optimal actions from there on. But Q star algorithm tells me that if I'm at state S and I necessarily select action A, and after that I behave optimally. So if I select the first action in the optimal manner, then I have the V star value. So V star is nothing but my max of Q star of ST plus 1A. Okay. So once I have that, all I need to do is substitute this in the equation, and a similar equation follows like we had in the SARSA algorithm. So you have your uh, Q of STAT is equal to Q of ST comma AT plus alpha T plus 1 comma max A prime Q of ST plus 1 A prime minus. Okay, so this is the Q learning update state. Okay.
Sir, on the left side, it's a Q star STAT, right?
Yes. Eventually, you will converge to Q star. But because this is also happening iteratively, no? So in the first step itself, you don't get Q star.
Yeah.
So after you do this, eventually you will end up with Q star. Even in SARSA also, you will end up with the Q star algorithm. But the equation that both are solving is different. One is dealing with the Bellman equation, other is dealing with the optimal Bellman. So since you're dealing with the optimal Bellman equation, you typically don't need a policy, because anyway you're taking a max, right? So if you have a max, you're not drawing any samples from the next action. So that's why it's independent of the policy. So that's why this is an off policy method. Okay.
Yeah.
And this thing, I think Sir had discussed this in class. So because uh, Q learning is trying to define the optimal policy, whereas my SARSA gives me the exploratory, or a more conservative policy. So my Q learning algorithm gives me this particular path, and yeah, so this is the path that I get from Q learning, because it doesn't care, okay, how many times you get a negative reward when you're trying to move around. It just cares for the optimal policy, because since there is no exploration, you try to take the best possible action and don't care about safety, right? But in your SARSA algorithm, it will try to be far away from the cliff itself, so that whenever you're even if you try to explore randomly, you don't fall off in the cliff. So if you're far away from the cliff, it's better for you. So you take this particular path and you, you get the policy, right? This is SARSA. Okay, so we'll just look at a code. Okay, I've written a code for this exact same scenario. We'll quickly take a look at that, and like how it affects if I change the number of training episodes. Before that, just I'll finish off this thing, the non-graded assignment part. So TD error is this part, and which of the following is true for TD0? It uses the full return. No, it just looks at the one-step return. Both TD0 and Monte Carlo evaluation converge to the same value function given a finite number of samples. No, this thing was discussed by Sir in the lectures. So if you have infinite number of samples, yes, they eventually converge to the same value function. But if you have, some limited samples that you can draw from, limited computational power. So some methods sometimes Monte Carlo policies have advantages, and sometimes your TD0 policy have different advantages. It depends on the problem that you're trying to solve. Okay, so this is the correct answer. Okay, so I think this was discussed. Pi is the estimation policy and mu is the behavior policy. Okay, and this is an assertion reasoning based question. SARSA is an on policy method. This is correct. In SARSA, we do not update the action that was used, so it is on policy method. In SARSA, we do not update the action that was actually used, so it is on policy. So this is incorrect. We are updating the action that was used, hence it is an on policy method. So the assertion is correct, the reasoning is false, and yeah, the assertion is true and the reasoning is false. Okay. Next up, which of the following statements are true? Learning requires at least a simulation model for the MDP. No, learning requires. Yeah, learning doesn't require a simulation model, because learning is something that you do on a real world setup, so you don't have some access to a simulation. The planning requires a simulation model, so you can play the same game different number of times and come up with a plan. And learning can be done using just the real world sample. This is true. Planning can be done. This is incorrect. Okay, so yeah, I think finished what I had for my slides. I'll just quickly share the screen. You can see my screen, right?
Yeah. Yeah, it's loading. Yeah.
Okay, yeah. So I'll just make this anyone with the link. Share. Okay. So this is a simple cliff world example. Okay. So I have 4 rows and I have 12 columns. Okay. The same that was used in the example given. So I start from 3,0 and I end at 3,11, exactly same as what the problem was showing. And I just try to I try to define the environment here. Okay, so this is the cliff environment. You initialize the start position, end position, and other stuff. These are the possible actions that you can take, and how you update the indices. This is the reward. So if you fall into a cliff, you get a reward of -100. Otherwise, you keep getting -1 until you reach the goal. And this is a function to show the board at each time instance. So this is the agent that is moving on the cliff. So the agents has the set of actions, go up, left, right, down. uh, states records the position and action of each episode. You have different parameters, and you have the choose action. So here we are using a simple epsilon greedy strategy for choose actions, and this is reset. So reset, brings my agent back to the start state. Uh, Play basically is the game that you're playing. So for each at each time instance, you select an action and you choose an action and you take the step and so on. You get a reward, and you try to optimize on that. Okay, so this is the basic function, and in the end we just show the route. Okay, after the game has ended, we just look at the route. Okay, so this is the SARSA training. So the exploration rate has been kept to be zero point 0.1. Here SARSA has been made true. And you can still see the screen, right? I just got disconnected here.
Yeah, yeah, okay.
Okay, so this is the SARSA training part. I'll just so I'm making it play 2,500 rounds. Okay, so once I do that, okay, so this is how my strategy looks like. Okay, so this is the route. So R is the route. So this is the route I get after 2,500 episodes. Let's say I play it again. Okay, this is moving here. Uh, it's moving here. Maybe if I increase the number of episodes, so if instead of 2,500, I make it play 5,000 episodes. It's not moving to the far top row. I mean, it's somewhere there. I just need to probably make the exploration larger. Yeah. Okay. Strange. It was happening before, but yeah. See, if I made the exploration 0.3, it's choosing a like safer path. So it depends on the exploration that you're doing and the number of episodes that you're training it on. So this is the SARSA implementation. Uh, Second is the Q learning implementation. I should keep the parameters similar. So here the exploration rate doesn't really matter, but this is we are doing it so that we have a goal directed or a focused update on the states that you are looking at. So we don't update all the states in the environment, all possible states, right? So this is the Q learning algorithm which has been used here. So here SARSA, you need to make SARSA to be false. So it's either SARSA is true or SARSA is false. Once I do that, this is what I get. Okay, so this is the optimal path that you can get for Q learning. Okay, and you will get this action even if I make it instead of 500, I make it learn only for 500 episodes or even less if I make it learn for 2,500. Yeah, 250 episodes. Uh, okay, 500 it's running. What happens at 250? Strange. Okay, maybe 250 is not enough. Probably it's just moving up down at a particular point. It's going up down between 1 comma 5 and 2 comma 5. I don't know why this is happening. Okay, works with 500. So this is the basic implementation, okay, for the cliff world problem. So you have the code for SARSA, you have the code for Q learning. Uh, okay, and second thing I wanted to show was this thing. I think Aniket already shared in the last lecture. And since you're the only one left, I should quickly run over it. It's similar. So I won't run the code. I'll run the code if and where it's necessary. Okay. So the problem statement is we are trying to implement SARS and Q learning on the grid world problem. On the grid world problem, you have this 4 particular actions, and the grid world looks like this. Okay. So you have some start location. You want to go to some goal location, and these are the rewards that you get. So this one represents. So the number that you have, you just take the negative of that. That's the reward you get on reaching that particular state. So if you reach these states in between, you get a reward of -2. If you reach these states, you get a reward of -1. Okay. So this is how the grid world looks like. So these are the 3 starting positions. The agents can get initialized at any of these 3 positions. The yellow box represents the agent's current position in the environment. This red and pink represents the rewards, negative penalty. So red is a danger area, pink is a relatively danger, like relatively safer than the red area, and green is the goal that you want to reach. So if I start from here, if I am doing Q learning, I don't care about accumulating negative rewards. I just go straight here. You take the shorter path. Okay. But if I use SARSA, I probably make a longer path, or try to go so that I minimize this thing. I'm looking at a safer solution in SARSA, right? So this is how the QL looks like. So this plot basically shows. Okay, I can share this. So the thing is, this code won't run by itself. Okay, so you need uh, some more uh, stuff also. So I have these 3-4 functions in the drive folder. So all you need to do is I'll share this data in the like in the folder that I have where I share the lecture slides and stuff. So you have this entire data. So this will be stored there. So all you need to do is when you go here, you have to load this files into your drive folder. So I'll upload a folder known as tutorial 3. You just download that folder and you upload it to your Google Drive, and then you execute, give the correct path. So in my drive, I have a folder named RL Totes, and then inside that I have tutorial 3. So I'll show how it looks. So I have this thing. So I have created a folder called RL Totes, and inside that I have this tutorial 3. So inside tutorial 3, I have these different things. Okay, so I'm just specifying the path to that. To run this code, I'll give this data. You just need to specify the path, and you can run the code. Okay, and yeah, so this is the Q plot. Okay, so it's a 3-dimensional plot. So the first 2 data represents the row and the column, and the third data represents the action. So you have 2 different exploration strategies. One is the epsilon greedy, one is the softmax. These 2 functions are there. Then first we look at the SARSA implementation. Okay, so this is the update rule for SARSA. So the hyperparameters here is alpha, epsilon, and the number of episodes. So here alpha is 0.4, gamma is 0.9, 10,000 episodes, epsilon 0.1. Okay, so we initialize the Q value, which is initially 0, and then when you train it, this is a SARSA function, and then you simply train it for 10,000 episodes. So initially all the Q values are 0, and as and when it trains, so after like Okay, so after like every 100 episodes, it will show the changes here. Okay, so you see with time, these actions are also changing, and this represents the confidence of the action. Okay, in the this represents the confidence of the action. So you see, this is since this is the goal state. So if you are reaching this state, you can say with like 100% confidence to go either to the left, right, up, or down, and the confidence decreases when you move farther and farther away from the goal. Right. Uh, So this is for SARSA, right? Yeah. So this is for SARSA. You would typically see actions that are, taking the longer route. So here, since this is a, negative reward kind of a setting, so this arrow is like in this states, it is better to move, towards the outer part and take the longer path to reach the goal. Okay. And
So this code also assumes that the wind and sleep kind of uncertainty.
what thing? What thing?
Like
Yeah, 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 yeah.
unfixed.
Yeah, yeah. It assumes that there is a point to uncertainty, and there is a westerly wind. Both these stochasticity are also there. I think it's depends on that, right? Uh, yeah. So the agent with point two probability takes a random action, like similar to the frozen lake case. In frozen lake, you had like one third probability of taking a perpendicular action. Here, it takes a random action with probability point two. So if I choose action, some action at time t, I only take that action with 80% probability, and with 20% probability, I take some random action. And then after every time step, there is a probability 0.5 with which the agent also moves an extra step to the right. Okay, so this probability keeps adding up with like with each time step, right? And yeah, so this is how the path looks like for SARSA. So you see, it tries to take a longer path since this is the area where you get a lot of negative reward. So in order to reach the goal, SARSA usually tries to take a safer path. So you see these arrows are pointing away from the negative reward part. And just to see the visualization, so the agent starts here. So instead of just going in this direction, the agent takes a more conservative path and tries to reach goal like this. Okay, so it took total 31 steps and got a reward of minus 95. Okay, uh, and then this is like analysis for the performance. I won't run it; it will take a lot of time. So, so here the same experiment you are running it for 5 different times, and the start position is different in each case. So since you have 3 different start states, so in each experiment you are randomly selecting a start state and doing this entire learning. So that, and then whatever you're getting, you're averaging that. So this is how the analysis looks like. So the number of steps to reach the goal state. So initially it took like a lot of steps to reach the goal, and with time, like with some few hundreds of episodes, you like require very limited steps to reach the goal, and you find a nice convergence over here. And same for the total reward. So in some few hundred episodes, you can get the best possible total reward convergence. Similarly, for Q learning, here since we're solving for the optimal Bellman equation, so it will try to select the optimal path rather than the safest path, right? So this will take 1 minute. Oh, okay. I thought this path would be more straighter. It's still pointing in the opposite direction. Okay, I think here the paths are straighter. I think this is the starting position, most likely. That's why this didn't get updated, because if it would have started from here or here, maybe the paths would have been straighter. Since it started here, it's going here. But yeah, we'll look at. Okay, so it started here, and it's taking. See, it's venturing into the red region. And reaching here. So the reason it took large number of steps, like more number of steps, because of the stochasticity involved, right? It moves with 0.5 probability to the right with each time step because of the Westerl events. So, okay, so this is the total reward in Q learning, the Q star learning. Okay, and again you repeat the same experiment. You see the total number of steps and the convergence of the reward. So this is a nice comparison for SARSA and Q learning. So you see there is not much of a difference for the problem that we're targeting. Like on a larger scale, if we look at the performance is more or less similar, right? But depending on the different type of applications or different types of environments people use, so one chooses either SARSA or Q learning. Like it is totally dependent on the application that you're dealing with. So yeah, I think that was all I had for today's class.
Yeah,
If you have any
just
question,
one.
yeah,
Yeah, one question, sir. So the earlier example which we have discussed, like the cliff example.
yeah.
In that, if we add, say for Q learning, it took optimum path just beside the cliff. So if we add
Mhm.
some kind of uncertainty or stochastic nature there,
Yeah,
that maybe a person can fall in from the cliff, or something like that when it passes
correct,
by just nearby the cliff.
correct,
If we
correct.
add that, will it take a little bit longer route, kind of?
Yeah, it should account. It should account into that. Uh, so there is no exploration, but there is this uncertainty. So because of that, it should try to move, like, let's say, one row up. But that also depends on the exploration part.
Okay, okay.
So the path won't be same for sure. So one interesting thing that you can try out is you have the frozen lake problem, right? That we
Yeah,
discussed last week. So
yeah,
you can define a similar thing, right? So frozen lake, you have holes and ice, you know. So
yeah.
you can define your frozen lake in a similar manner. So you have the stochasticity there. So you can try out, right?
Yes, yeah. Okay.
So you have the code. You just need to design the environment or whatever is there. Uh, Not even the environment, just the configuration, and then you can see the results for yourself. Yeah.
Yes, yeah, yeah. Okay.
Okay. Okay. I think that's all from my end. Uh, Thanks for
Yeah,
attending.
yeah.
Okay. Bye.
Thanks a lot, sir.
Good
Bye.
night. Good night. Bye.
Good.